Welcome back to Mathematics with Armin. In this part 2 of Fundamental Counting Principle, we're going to look at applications with regard to committees, passwords, PIN codes, numbers, and then we're also going to look at some probability applications where the counting principle will be required. Thank you very much. In part 2, we're going to just briefly go over the concepts we did in under fundamental counting principles and some of the rules we use for arrangements, because we'll be needing it for some of the problems in part 2. Part 2 specifically, we're going to look at counting how committees can be elected, and then we're also going to look at passwords, PIN codes, and numbers, and then we're going to take some problems that involves probability. And here we also have an exercise worksheet with some additional exercises. Let us just briefly go over some of the counting principles and the rules we did in the part 1. So because you will need that to continue. Now we can actually deduce a rule that we can use there. If an event can be done in m ways, let's say the one event can be done in m ways, right? And then a second event can be done in n ways. And then we have a third event or task that can be done in k ways. Now to find the total number of possible outcomes for these three tasks, we just find the product of the three. So I have to find the product of the m, the n, and the k. That means there we have it, m times n times k. And because we use product, this rule is also sometimes known as the rule of product or the product rule. So it's just m times n times k. If there's a fourth one, it will be just times the other one. And that is our fundamental counting principle. Let's just look at our rule here. If three events can be done in m ways, n ways, or k ways, then the number of choices to do one of these events is the sum m plus n plus k. So in the rule of sum, we have event E1, we choose between event E1 or E2 or E3, then we have to add the number of choices, right? If you have to choose one of these events. And rule of product would be that you have event E1 and event E2 and event E3, then we multiply the number of choices here. So in the case of sum, we have or, then we have or, then we'll add. If we have and here, then we multiply our choices. Now, based on those two examples, we can then generalize. So we can see that if we have n different objects, important they must be different, they can be arranged in n factorial ways, right? For example, if I have 20 different objects and I want to arrange all 20 of them, they can be arranged in 20 factorial ways there. So then we had the other case there, we would want to arrange some of the different objects, like r of n. So that will be n factorial, and then we find the difference between them, and that will give us the number of different arrangements we'll get if we just want to arrange a certain number of the different objects there. Now let's formulate a general rule for arrangement of objects where some of the objects are identical. So if we have n objects and we've got object R where there's some repetition, and object P there's some repetition, and object K where there's some identical, right? There could be more than one K, more than one occurring of that particular object. How can they be arranged? And we then have n factorial, that's the number of objects, and because of R, so we have small r factorial and small p factorial and small k factorial. Let me just explain the lowercase here. The n there is quite clear. N is actually the number of objects that you want to arrange, right? Then this small r is the number of object capital R, right? So capital R, let's say there are 5 of those objects identical, then this will be 5 factorial. And the same there's capital P, and the number of objects of capital P is the lowercase, and the number of object k that are repeated, that's lowercase there, and that is what we now have, right? So that's the number of identical objects R, P is the number of identical objects P, and K is the number of identical objects K, right? So that's our formula, which we have arrangement of objects, and some of the objects are identical, and we compensate by dividing. Now from the example we can see that arrangement of different objects, if repetition of objects is allowed, we can actually form a very simple general rule. If R of n different objects can be arranged into the exponent R different ways, if repetition is allowed, right? It's into the exponent R, so we actually get a power here. Now this next unit we're going to show counting, the electing of committees. How many, we can count the number of ways of electing committees. Now we're going to look at examples where we can count the number of ways committees can be elected. Let's take this example here. This company's board consists of 6 male and 4 female members. Otherwise, how many? They've got 10 members there. Now, an executive committee consisting of a vice president, a vice president, and a treasurer needs to be elected. Determine how many ways the executive committee can be elected if, first of all, there are no restrictions. P, there's a restriction now. The vice president must be female. C, it must be a mixed gender committee. And at most 2 female members need to be on the committee. So let's look at that. Now let's look at the first question there. Remember, we have 6 male and 4 female members, and the president, then the vice president, and then a secretary must be chosen in that order. So first of all, there are no restrictions. So let's see there. So there's 3 things that need to be done: a president, and then a vice president, and then a treasurer. How many people are there all together? That's correct. So it can be any one of the 10. Now, if a president is, a person can't be president and vice president. So there's actually 1 less. So there are 9 ways of choosing the vice president. And in other words, 2 people have already been elected out of the 10. That leaves us with 8. So in other words, there we have 10 times 9 times 8. If we calculate that, there are a total of 720 ways in which we can elect the president, the vice president, the secretary from 10 members there with no restrictions. Now let's consider the second question. In this question here, there's a restriction. It says here the vice president must be female, right? So we then have choices here, and these choices just then depend on the gender of the president. Let's just see what we mean by that. If I have a male president, right, or we can have a female, so we have to look at those 2 situations here. If I have a male president, it means the vice president then has to be female, according to that restriction, and then we have to choose the secretary, right? So how many males do we have to be president there? It could be any of the 6. How many females do we have? 4. How many members do we actually have? 10. How many have been already elected? 2. So there's a remainder of, so any of the 8 there. So that's the number of ways we can have a male president. Let's look at the situation where we have a female president. This means that the president is female, but according to this restriction, the vice president still has to be female, right? So how many ways can we choose a female president? Any of the 4? Now 1 person's already been used, so the next can be 3. So we have 2 out of the 10, so we have 8 that can possibly be secretary, right? And so it's going to be the male or that, so we have to add those options there. So this is 6 times 4 times 8 plus 4 times 3 times 8, and if we calculate that, that's going to be 192 plus 96 equal to 288. Now let's consider our third example. In this one here, there is a restriction. It says the committee must be mixed gender. In other words, it cannot consist of males only, it cannot consist of females only. And at most 2 female members need to be on the committee, right? At most. So let's see, what do we mean? What do we understand by at most 2 females? At most 2 That means it can be 2 females on the committee, it can be 1 female on the committee, or it can be no females on the committee. But it cannot be 0, because if there's no females, it means it's not a mixed gender. So the only options are there are 2 females or 1 female. So let's now look at the options here, right? So the committee has to consist of 2 females or 1 female. So let's look at that. So it'll be 2 females and 1 male, or it can be 1 female and 2 males. Let's look at the option, the first one there. To choose a female, there are 4 females, can be any one of the 4. And a female is chosen, so the next position can be filled by any of the remaining 3. Now, the third position then has to be filled by a male, right? So how many males are there? 6. Let's look at the other option here. Here we have 1 female, so it can be any of the 4. Now for the other 2 positions, we can only select from the males. So that's going to be, can be any one of the 6. So that will be 6. And then 1 male has already been elected, so it can be any one of the 5. You cannot fill 2 positions or 3 positions at the same time. So there we're going to apply the sum rule again because of OR. So the number of election options here is the sum of those 2 choices there, and that gives us 72 plus 120, which is 192. Now we're going to look at another example where you have to count electing committees, but this is going to be an example for you to try, right? So let's see, there's the information. We have 6 learners from 2 phases, FET and the G. FET, as you know, is grade 10, 11, and 12. GET is at the high school is going to be 8 and 9. And they're going to form a learner representative committee. Now they want to choose a chairperson, a treasurer, and a secretary, and it must be elected in that order. So here we have some questions. Determine how many ways can this 3-person committee if there are no restrictions. And here we have the chairperson must be an FET learner, right? And then a 3-person committee must consist of learners of both phases. Otherwise, it can't just be the FET learners being on the committee or the GET being on the committee. So let's look at that. Now, this is going to be an example for you to try. So let's just get the information first. 6 FET, and we have colors just to assist you, and 6 GET learners. So the counting will be for you. There are no restrictions. So we're going to look at the solution, but let's pause the video and give you a chance here. This one is not that difficult, so let's make it 2 minutes, but you will get about 2 marks for that. So let's pause, and then once you're done, then you can continue again. Okay, so let's see, look at your solutions now. We want to choose a chairperson, a treasurer, and a secretary, right? And there's no restriction. So how many people do we have available to be chairperson? It can be any of the 12. So 1 person's already been elected. Then to be treasurer, it can be any of the 11. So already 2 people have been elected. And the remaining position can then be filled by any of the other 10. So that's our total number of choices there. And if we calculate that, so that's 12 times 11 times 10, it's 1,320. I hope you're ready for the next question. So again, that's just our information there. Here's the question. The chairperson must be a FET learner. Okay, so you have to find the solution, and you will pause the video now, and let's give you 3 minutes to do that. It will be worth about 3 marks. So pause the video and then we'll start again. Okay, you ready? So let's see. We want to choose a chairperson, a treasurer, and a secretary. Now, if the chairperson must be an FET learner, it means must be chosen out of the 6 FET, so it can be any of the 6, right? Now the chairperson, so 1 person's already been elected. Now the remaining position can be filled by any of the remaining. The second position can be filled by any of the remaining. That's correct, 11. Okay. And then the next one can be filled by the remaining 10. So in this case here, the election options are 6 times 11 times 10, which is 660. Now we look at the last question here. This one that you have to do. A 3-person committee must consist of both phases. In other words, it shouldn't consist of FET or only or GET learners only, right? So there's a solution, and you suggest you pause the video, try it, and then once you have it, then you can continue just to see how the compare your solution with the actual solution as well. So pause, and 3 minutes should be more than enough. Okay, let's look at your solutions now. So we have to look at the options first. We see how many ways can we have the committee be elected that they only consist of FET or only of GET. So let's look at that first. If they consist of FET, so I'm using the green for FET. In other words, everybody is elected out of the FET group. So there's 6 there, then it's 1 less, it's 5, and then 4, and that gives me a total of 120. Let's look at the GET, and it's exactly the same because it's the same number of learners there. So it's 6 times 5 times 4, and that gives me 120, right? So in other words, there's a total of 240 cases where it consists of only FET and only GET. But we want to actually determine where it does not consist of the one group exclusively. So let's look at the case where we had no restrictions. When we had no restrictions, we actually had a total of 1,320 ways that we could elect them. Now, to be able to find the number of ways that the committee will consist of learners from both phases, we take the 1,320 and we subtract the cases where it was only FET and GET. So we subtract, and because it's OR, it means 120 plus 120, and we do that calculation, it now gives me 1,080 there. We're going to do the last type of counting questions here. This will be counting number of passwords, number of PIN codes, a number of 2-digit or 3-digit or 4-digit or any specific number that's required there. Let's look at our first question. Here we're going to start with passwords. So we have a 6-character passwords, which you should be familiar with. And now they tell you actually how the password needs to be constructed. There must be 2 single-digit numbers, followed by 2 lowercase letters, followed by 1 uppercase letter, and followed by one of these special characters, right? So there we have questions. No repetition is allowed, repetition is not allowed, and then we have on. So we're going to look at each one individually. Let's look at our first example here. We've got a 6-character password. There we've got a question that must consist of digits, and we know those are our digits there. And there we have our letters of our alphabet, just to make sure those are lowercase and those are uppercase, not the ones necessary at the end. And then we have our characters that we have there. Okay, now let's see. First of all, they say repetition is allowed. So we want a 6-character, so we just note repetition is allowed. So you should highlight that. So let's look at our solution now. We have a 6-character password, so we fill the 6 spaces that needs to be filled. So we start off with a digit. How many digits do we have? Any of the 10. Because repetition is allowed, I can use any of the 10 again. How many letters of the alphabet are there? In the English alphabet, 26. And repetition is allowed, so the next letter can be any of the 26 again. And then we need the uppercase, and because repetition can be any of those 26 letters as well. Then I must choose one of the characters, and how many characters are available? Any 4. So that is the number of passwords I can make if there's no restriction based on that information. And if we multiply that, you see it's quite a large number, 7,030,400. Let's look at the next question and see what is actually required here. In this case here, we need to find the number of passwords, but repetition is not allowed. Okay, so that's important. You have to note repetition is not allowed. So if you use one letter, you can't use it again. If you use one character, you can't use it again. So let's see. So it's always important to deal with your restrictions and note what you have there. We have a 6-character password. So how many digits do I have available? 10. I already used one of the digits, so the next digit can only be filled by any of the remaining 9. How many letters of the alphabet do we have? 26, but now we're using up one of the letters, so that's 25. Now for uppercase, it's one of the letters. We already used 2 of the letters. That means I have 24 there. Characters, I haven't used characters yet, so I can choose any of the 4. So the number of passwords we can make with no repetition is allowed would be 10 times 9 times 26 times 25 times 24 times 4, and I'm sure you need a calculator to do that. That gives us 5,616,000. Always important to sort out your restrictions. Try to understand what your restrictions are there. Let's do the last question here. Last sub question. There's our given information. There's our characters. Right? Let's just see what we have there. No repetition is allowed. So that's one of our restrictions there. Right? No repetition is allowed. Furthermore, they say the uppercase letter must be a vowel. What are the vowels? How many vowels are there? That's correct. There are 5 vowels, and those are the vowels A, E, I, O, U. Okay. Then they say the number. So if the repetition is not allowed, it means if I already use the vowels there, I can't use the vowels when it comes to lowercase as well. So they can't use a A, can't use a E in lowercase, or a I, or a O, or a U. There's another restriction. They say the number 0 is not allowed. Maybe a reason, 0 and the letter O looks very much the same, right? So it's sometimes better not to use both. You can easily make a mistake. Is it a 0 or is it a O? So they say 0 is not allowed. So if there's going to be a symbol, we know that's going to be a vowel, not a number. So if 0 is not allowed, we don't have all our 10 digits. We only have 9 digits available there. So it's always important to understand your restrictions there. So let's see, we are going to create the 6-character password. How many digits do we have available? Now we only have, that's correct, 9. Repetition is not allowed, so now the next digit can only, we've already used up one of the digits, so we only have 8. Now we come to the letters. How many letters are there in the alphabet? 26, but 5 of them are vowels. So how many are non-vowels? Okay, and that is 21. So we only have 21 letters there. Now we've used one of those 21 letters. Now we only have 20 to use there. Now they say the uppercase letter must be selected from the vowels. So how many do we have? That we have 5, and the characters here can be any of the 4. So to find the total number of passwords made with those restrictions would be 9 times 8 times 21 times 20 times 5 times 4. I'm sure you'll need a calculator for that. If we calculate that, that's 604,800. Now we're going to look at counting PIN numbers. You all should be very familiar with PIN numbers. You need a PIN to access your cell phone. You need a PIN to access your laptop. You need a PIN maybe to enter a venue or to open a lock, etc. Now, but this particular PIN here, we're not going to use all the digits. So it's only these digits that will be required to make that PIN. And there we have some questions there, and we're going to look at each of these questions in the next slides. Now let's look at the solution, and let's look at the first one. We want a 5-digit PIN code, and it needs to be developed using those numbers there. So there's our, and we want to crack that code. So see how many options do we have. First of all, they say repetition is allowed. Okay, so repetition is allowed means I can have an example here, 1 1 1 1 1, as they have there. See, that's nice example. Repetition is allowed. So I want 5 digits, so let's say I have my spaces there. The first one can be any of the 7. Because repetition is allowed, 7 1, second one can also be any of the 7. Any of the 7, any of the 7, any of the 7. So the number of choices I would have here would be 7 to the exponent 5. And 7 to the exponent 5, 16,807. Let's look at our next question here. In this one here, repetition is not allowed. So let's see here. In this case, it says that repetition is not allowed. So let's see there. So you always have to deal with the, make sure you understand your conditions. No repetition. Okay. So let's look at our choices here. We have 7, so that will be times 5, 6, and then 5, and then 4, and then 3. Simple there. You find the product of that. And the product there is 2520. Let's look at this password with these requirements here. It says the code must end with an odd digit and no repetition is allowed. Okay, so let's look at the conditions. Always make sure you understand your conditions. It says odd number. So what are the odd numbers there? 1, 5, and 9. So we only have 3 odd numbers. It can be any of the, and that means it must end with an odd digit. And there must be no repetition, so you need to bear that in mind. So let's start with the positive one first, right? So if it ends, let's sort this one out first, right? Let's look at the positive condition here. There are any of the 3 could be my end digit. Now, because I have 7 digits, I already filled up 1. That means I only have 6. Now I already filled up 2, so I have 5. I already filled up 3, so I have 4. And then filled up 4, so I have 3, right? So that is the number of options I have if the code must end with an odd digit and no repetition of digits would be allowed. And that gives me the value 1080. Let's look at another digit problem here, but in this case we're going to look at numbers, not digits. We say a 4-digit number, not a pin code. And here we have some questions. Digits can be repeated, not repeated, and we're going to look at each one individually. Let's look at the first question here. We want a 4-digit number. So those are the digits we can use. And it says the digits can be repeated. So let's look at the solution here. But we always have to make sure we understand the conditions. Repetition is allowed, but the 10 to the 3rd digit, the 1000th digit, cannot be 0. For example, a number like this, 0, 1, 2, 3, 4, I'm using 4 digits, but if I have a 0 in front there, that is not regarded as a 4 digit, it's only regarded as a 3-digit number. So we cannot have a 0 in that. That's units, tens, hundreds, and thousands. So the 10 to the 3 place value cannot have a 0 there. So let's look at our options now. So the spaces. So in other words, here I cannot have a 0 here. So how many options do I have? I have any of the 9. But then for the 100th digit, or that place there, I can have any of the 10, and any of the 10, and any of the 10. That's repetition is allowed. So in other words, the total number of 4-digit numbers I can have is exactly 9,000. Now let's just look at the second question required here. There's our digits available. It says here the digits cannot be repeated, right? But as before, we must remember one of the essential conditions here is that the 1000th, 10 to the 3rd place there, you cannot have a 0 in that position, as we illustrated previously. And here they say no repetition. So there's 2 negative conditions here. So let's start with the first. I cannot use a 0 there. So there's only 9 options. How many numbers have I used up? I used up 1. So how many do I still have left? That's right, still have 9. How many have I used thus far? 2. So I have 8. So I've used up 3 of the numbers. So I still have 7. So if digits cannot be repeated, I have 9 times 9 times 8 times 7. And that gives you 4,536. Let's look at the third example question here. There's my digits there, and now it says the number needs to be even and the digits not repeated. So let's make a note of that. So our conditions here is it must be even, and what will indicate it even? The unit digit there. And so in the unit digit I can either have a 0 or a 2 or a 4 or a 6 or a 8. Okay? But also remember that it says there no repetition is allowed, and we must not forget that in the thousandth place value there I cannot have a 0. Now you see in the units I could possibly have a 0, and in the thousands I must be careful about the 0. So we seem to have a conflict there. So it's important here that we try to sort out the positive condition. And what is the positive condition? Being even. Right? So always it's advisable to start with a positive condition there. So I can have in my units digit, I can have a 0, and the other option is not to have a 0. In other words, I can either have a 2 or a 4 or a 6 or a 8. Right? Let's look at the case where we have our units digit 0. You see, that's the units digit. So if I put a 0 in there, I've already used up. There's only one 0, so it could be 1. Now, how many numbers do I have available? Digits do I have available? 10. So I used up 1, so I can have any of the 9 there. How many have I used up thus far? I've used up 2, so I still have 8. Now I have 7. So if I want to have a 4-digit number ending with a 0 with no repetition, I have this many options there. Now let's look at the other case where I could have the unit either being a 2 or a 4 or a 6. So I've got 4 options there. I used up one number, but remember I cannot have a 0 here, right? So I have 9 minus 1, so I only have 8 options that I have there. I used up 2 of my numbers, so I still have 8 left. I used up 3, so I have 7. And because I have an OR, I'm going to apply the sum rule there. So it's going to be 9 times 8 times 7 times 1. And then I find the sum with 8 times 8 times 7 times 4. That gives me 504 plus 1,792. It gives me a total of 2,296. Right? So it's always advisable when you have this here to start with a positive there. Even, so you can see where should the even be. Right? It doesn't mean you always have to start from thousands down to units. It depends on the question there. And here I have options to choose from. Now let's look at the last one. This one is a little bit more challenging. So let's see, there's our numbers available, and now it says that there's our question, and now we're going to start. Always look at your conditions. The number must be less than 4,000, right? So that's important. That's a positive condition, right? And now we have a negative condition, not to be repeated. So I must bear that in mind. And I also have one, it cannot be 0, right? So maybe it's good to start then here with the positive condition. What does it mean if it must be less than 4,000? In other words, the thousands digit can be a 1, a 2, or a 3, right? Because I can have 1,000 and something, which will be less. I can have 2,000 and something, or I can have 3,000 and something, right? So those will all be possibilities there. So in other words, if I have my thousands, I have 3 possible digits I could use there. So I have 3, right? And I have 10 digits available. So I already used up one of the digits, so I can put any 9. Then I can have any 8. Then I can have any 7, right? So if I want a number less than 4,000, I now have a total of 3 times 9 times 8 times 7, which gives me a total of 1,512. Let's do one more based on the 4-digit number. So I want a 4-digit number, and it must be created as follows. The number must be exactly divisible by 5. Right? There must be no fractions left, exactly divisible. And there should be no repetition. So exactly divisible is a positive condition. Okay. Now, if a number is exactly divisible by how do you know a number is exactly divisible by 5? That's correct if the unit digit is either a 0 or a 5. No repetition is negative, so I need to start with my positive condition, right? Always best to start with the positive condition. So in other words, the unit digit can be a 0 or a 5, right? So I have the option of the but because I have the 0 and 0 is also there, you see 0 could be in the units place, and it also I need to be aware of it when I work with the thousands. So it's best to separate the two. So I'm going to look at the option where my unit digit is a 0 and the other option where my unit digit is a 5, and I'll find the sum of the two. So if I have a unit digit of 0, so if I use the 0, there's only one 0, okay? And there's only one 5. So let's see, there's 1 0, and then there are 10 numbers, but I already used up a 0, so I can use any of the other remaining 9, right? I've used up 2, so I have 8. I've used up 3, so I have 7, okay? Here, if I have a 5, I start with the point, I cannot put a 0 here. So I've got 1 and the 0, so there's 2 numbers I cannot use. So there, I'm still left with 8 options there. Now I've used up 2 numbers already, but I have 10 available of those digits. That means I will still have 8 more. And then I have 7. And we're having the choice between having a unit digit being 0 or the unit digit being a 5. And then I'm going to use my sum rule, so that I'm going to find the sum of those options there. And if we calculate that, that's 504 plus 448, that's 952. Now we're at the stage where we actually want to apply our counting to probability questions, right? Remember we said at the beginning, sometimes you have to count to be able to do the probability. So we're going to show you how we can use some of our counting techniques and apply it to some probability situations there. Let's look at our first question here. Here we have the letters of the word multiple, and we assume the letters can be arranged randomly. And now we want to calculate the probability, right? Not the number, the probability that the word arrangement, in other words, using all those letters, will start with a T and end with a T. Then we have another probability that the vowels, so I need to know what vowels are, they are placed next to each other. What would the probability be that the vowels will be placed next to each other in a word arrangement? Okay, so we're going to look at that. Okay, that's we have got the word multiple, and we want to find a probability here. So let's see. As we can see, there are 8 letters. 6 of them are different, and we've got 2 L's. So how do we arrange 8 letters? If we have 2 L's, that will be 8 factorial divided by 2. You can leave it like that, but it's not such a large number. That's 20,160. Now, if the T and E are fixed, that means only 6 of the letters need to be arranged. Just look there. We start with the T and end with the E. So the T and the E is already fixed. You know, they don't move around. So it's only 6 letters. But recall those 6 letters, 2 of them are L's. So we also have to do that. So arranging the T and the E, there's only one way it can be done. Start with the T, end with the T. The other 6 letters are 6 factorial. They were different, but there are 2 L's, so it's 6 factorial divided by 2. Therefore, the number of arrangements I have there, 6 factorial divided by 2, which is in this case 360. But recall that we didn't ask you to count, we want the probability. And we know the total arrangements for 8 letters is 20,000. So the probability there would be 360, because that's the case where it starts with a T and end with a E. And that's the, without any restrictions there, that's the 8 letters that can be arranged. And if you simplify that, it gives me a probability of 1 over 56. I recommend that you leave the number here in common fraction form, right? Do not round off unnecessarily unless this question specifically requires you to give it to a certain number of decimal places. Let's look at the second question here. We want to determine the probability that vowels will be placed randomly next to each other in any word arrangement. Right, so it's a random arrangement of the letters. We've got the word multiple, and we still recall there are 6 different letters and 2 L's. Now I say the number of arrangement of those 8 letters, considering there are 2 L's, is 8 factorial divided by 2 factorial. It gives me 20,160. Now here we want the vowels together, so if there's 3, and you can see there are 3 vowels. Those are the vowels U, I, and E. So if there's 3 and there were 8, so they've got 5 letters there, right? And you know, of those 5 letters, 2 of them are still L's. So in other words, those are my 5 letters, and I have my 3 vowels. So in other words, I've got 5 plus the group of vowels, so there are 6 objects that need to be arranged, right? Those vowels always stay together. So it's 6 objects with the vowels. 6 objects can be arranged as 6 factorial, but because the 6 also contains 2 L's, I divide by 2 factorial. And now the vowels, those 3 vowels can also be arranged, and there's 3, so it can be arranged in 3 factorial ways. So therefore the number of arrangements of 6 objects with vowels placed next to each other would be 2,160. Now for the probability, it would be 2,160 over the total number of arrangements, and that is, by simplify that, gives me 3 over 28. Let's do one more question here. We have 5 couples who are seated together in a row, and the couples always want to sit next to each other. Let's say it's husband and wife, they always want to sit next to each other. How many people are there all together? That's good. A couple is 2, so there are 10. Determine the number of unique ways that these 5, so we just want to arrange the couples. Okay, let's look at the first question there. So it's 5, we want to arrange the 5 couples, and 5 couples can be arranged. So there's 5 couples, and that's 5 factorial. But you know, each couple itself consists of 2 people. You can have the husband and the wife, or you can have the wife and the husband sitting. So each couple there. So the 5 couples can be arranged in 5 factorial ways. Couple number 1, 2 factorial. Couple number 2 can switch. You can have Mr. and Mrs. or Mrs. and Mr. You can have John and Mary, and you can have Mary and John. You can have Tandeka and Tabo, and you can have Tabo and Tandeka. So there I have my arrangements. There will be 5 factorial, and the couples are all the same, so that's 2 factorial, 1, 2, 3, 4, 5. It's repeated multiplication. I just write it as 2 to the 5. If we calculate that, that gives me 3,840. Just recall here, this is just a counting, not a probability. Let's do the second one here. Now they say the 2 couples will not sit next to each other. There's a little bit of a negative restriction there. So let's see here. 2 couples not to sit together. Okay. Consider, so when you have a not to, it's always better to do the opposite. Let's consider them sitting together. So there's the 2 couples. How many people are there all together? 4. So if there's 2 couples, there's 3 more couples that needs to be seated. So it's couple 1, couple 2, and couple 3, and this group of 4. So that's 4 objects that need to be arranged. So there's the 4 objects, and then these 2 couples can also be arranged, right? There are 4 people there. So how can couples? There's 2 couples, so I need to arrange 2 couples can be arranged in a certain way, and then each couple, remember there are 5 couples, they can also be switched around still. So there are 4 objects, that's 4 factorial, right? 2 couples can be arranged in 2 factorial way. Each couple can be arranged in 2 factorial, can switch them around, but there are 5 of them, so I raise repeated multiplication, raise it to the 5. We do that calculation, it gives us 1,536. The number of ways of 5 couples sitting together is 3840. but we want a probability. 5 couples sitting together, that is 5 factorial, right, which we worked out from the previous question. So the probability there would be, if I want to work out how many of them are not sitting together, it's when they do sit together, just when the couples are arranged, that's the way couples can be arranged in 3,840 ways, and I remove the number of cases where they do sit together, and that will tell me how many. So if I calculate that, I can keep it like that. So it's that over the total number of ways in which they can sit together, right? And if we simplify that, it's 3 over 5. You can calculate that, or you can just leave it in that subtraction form. I just wanted to show you that that is actually this value here, right? So whenever you have something like not sitting together, then you just look at the case where they do sit together, okay? Or sometimes they say not more than 500. So let's say, let it be less than 5. Just do the opposite then, or equal to that value there. Now this is our last question. It's reminding us that we're back at school. We have 5 mathematics books and 4 accounting books and 3 chemistry books and 2 physics books and 1 biology book. Must be arranged. You can see I have this in different colors. This is also to remind you, highlight the information so it stands out. 5 maths, 4 accounting, 3 chemistry, 2 physics, and 1 biology, and they're all different. That's important. They're 5 different books there. Determine in how many unique ways can all the books be arranged, but they want to keep the subject books together. They want the books mix, a maths book and then accounting, keep all the maths books together, all the accounting books together. And then we have a question here on probability. So let's look at the first one here. So that's just our information, and we remember the books are different. Okay. And we want the subject books together, but now they tell me something else. You want to keep the subject books together, but always keep chemistry and physics together as well, right? You don't want another subject between physics and chemistry. So there's an extra thing. So let's look at the positive things here. There are 5 subjects, and so there's a total of 15 books altogether. Okay. So we want to keep the physics and chemistry books together, and then there are 3 other subjects. There are 5 subjects. 1, 2, 3, 4, 5. So there's the 3 subjects, and that makes 5. So this is actually 1, 2, 3, 4 objects that need to be moved around. So it's those 4 objects that needs to be moved around. Those are the 2 subjects, physics and chemistry. Then each subject, there are 5 books. Those books can also be arranged. The accounting books can also be arranged differently, different ways. The chemistry books, and then the physics and the biology. There are 4 objects that can be arranged in 4 factorial. They're different. 2 subjects and 2 different subjects is 2 factorial. Maths books, 5 different maths books, 5 factorial. 4 accounting books, they are different, 4 factorial. 3 chemistry books, 3 factorial. 2 physics books, 2 factorial. 1 biology book, 1 factorial. So I just find the product, and the product there, as you can see, is quite a large number. It's 1,658,880, right? You can see it helps you to have a little bit of a diagram or put in some slots so you understand there, right? It really helps. They say physics, just put them together like that. If you put them in a bracket, then you can count. There's the mathematics, and there's the accounting, and there's the biology, and with them together, it's 4 objects that need to be arranged. Now let's end up with our last question here. Beautiful question. So if all the books are arranged randomly, determine the probability that the biology book will be in the middle and the subject books are always kept together. Now if the biology book is in the middle, that means I have how many books? I have 15 books. So there are 14 books except the biology book. And if it's in the middle, how many books on the left? 7 books on the left and 7 books on the right. Now which subjects would make 7? Maths and physics and accounting and chemistry. So that's my possible. The biology is in the middle, so I can only have maths and physics on the left and accounting and chemistry on the right, or the other way around, right? So that's the arrangement there. The biology is in the middle, so it's actually fixed. So there we have two objects, the left and the right. So that's the two pairs that I have there, right? The pair, that's a pair, as a pair, and there's a pair, so that's the two pairs. Then the maths and physics can be switched around. It can be physics and maths, accounting and chemistry, chemistry and accounting. Then we have the maths books itself, the accounting, the chemistry, the physics, and the biology books can be arranged as well. So let's see, two pairs can be only arranged in 2 factorial. Maths and physics is a pair, so that's 2 factorial. A and C is a pair, so that's 2 factorial. How many maths books? 5 factorial. Counting, 4 factorial. Chemistry, 3 factorial. Physics, 2 factorial. Biology, only 1, so it's 1 factorial. So we find the product of all of that. That gives me 276, 480. But how many ways can we arrange the books so that all the subjects are together? So there are 5 subjects, that's 5 factorial. The maths can be arranged, the counting, the chemistry, the physics, and the biology, and that gives me 4 million there. So if we find the probability, it's going to be the 276,480 over 4,147,200. And if we simplify that, it gives me 1 out of 15. Now we come to the most important part, the exercise worksheet, right? Before you start the exercise worksheet, I always advise that you go through these examples again. You know, look at the example, pause it, and then try to do it on your own, and then you can check, right? So go through them first. Don't just start with the exercise. And the examples I've taken from the exercise, I've actually taken it from external question papers, Department of Basic Education. And exactly, maybe just here and there I maybe adapted it slightly. So we'll just quickly look at that. We're not going to look at the solution, we're just going to look at 2014. There they have a password question there, and they say maybe something similar. The password must start with a D and end with a L. There we have 7 cars there, and you know, so there we have parking, arranging the parking. Let's look at 2016, 5 boys and 4 girls. They need to be seated, and there's some restriction. 1 boy and girl is a couple, so they want to sit together. And then you have a probability there as well. Let's look at 2017. There we have a coding system, so there we have to make some codes or passwords, and they have some restrictions there, right? Then they say it must be 2 letters followed by 2 digits, and then you know, there's some questions relating to the number of options we have there. In 2018, there's an arrangement of athletes, you know, some restriction, and then here we have a question on probability there. Thank you very much for watching my video. I really appreciate that. I'd also recommend that you view the other videos that I've made. Recently I have three-part on finance, and I've got videos on calculus, videos on inverse functions, and there's videos on trigonometry and analytic geometry and geometry as well. And please subscribe to my channel. And my channel is Maths with Armien. Thank you very much.